Hello dear students, you all are most welcome. I hope you all are doing great. Here in this session of today, I'm going to explain to you the derivation of the kinetic gas equation. That is the one you can see on the screen. P is equal to 1/3 rho Vrms squared. So this derivation is in fact the most important derivation of this chapter, which is purely based on the assumptions or the postulates of the kinetic theory of gases. In 1873, almost after 70 years of Dalton's atomic theory, a group of scientists, out of whom the chief were the Maxwell and the Boltzmann, had put forward some formulations which are known as the kinetic theory of matter. So out of the three states of matter, it is the gases which do have the maximum kinetic energy. So specifically in this chapter, we shall focus on the kinetic theory of the gases. There are a number of postulates or assumptions of the kinetic theory of gases which are quite important for us to understand and are important as well for this equation to be derived. So without any further ado, let's get into the derivation stepwise. But before that, just want you to know the quantities which are represented by the symbols which you can see in this expression. That is, P represents the pressure of the gas. What is pressure? We know the average force exerted per unit surface area of the wall of the container. Rho is normally the density of the gas. Vrms means the root mean square velocity of the gas. This has to be clarified a little in order to make you understand. Have a look at the screen now. So this is, for example, a container in which a particular gas is kept, and just assume that n number of similar molecules of the gas are enclosed within this container. Alright, so this is just a closed container which is filled up with a particular gas, and there are n number of similar molecules of the gas contained inside. Alright, so if the velocities of the molecules of the n molecules which are enclosed within the container be somewhat like V1, V2, V3 and so on up to Vn, n number of molecules are here na. If the velocity of the first one be V1 and that for the second one be V2, that for the third one be V3, and in this way the molecules are moving at random with different velocities in different directions, right? And the velocity of the nth molecule be Vn. Alright, so now just imagine that the one postulate of the kinetic theory of gas is telling that the molecules of a gas are constantly in random motion along straight line paths inside the container in which it is kept. So unless we make some kind of average, we cannot actually get an idea about the velocity of its molecules as a whole. We felt the need to make some kind of average, so that is how we did it. It is RMS, root mean square velocity. The thing that is actually is done over here is to find the root of the mean of the squares of the velocities of all the molecules comprising the gas. So in order to find this Vrms, we need to start from the end. Root means square, so let's start from the square. We need to square up the velocities of the individual molecules. So I'm squaring the velocities of the individual molecules of n number. First one was V1, so V1 square. Second one was V2, it's V2 square. Third velocity of the third one was V3, V3 square. In this way up to Vn, so Vn square. Okay, so not only making the square, we need to find the average, that is the mean of the squares, the root of the mean of the squares. So mean of the squares means we need to find the average of the squares of the velocities. Now how to find the average? Average is something we can find out by adding some items and dividing the sum by the number of items. So we are adding the squares of these velocities. Alright, we are adding the squares of these velocities, and we are supposed to divide the sum of the squares by the number of molecules. That is how we find the mean. Alright, so finding after the mean is not enough. Again, we are taking the square root of the mean. Square root of the mean. So find the square root of the mean. That is the average of the squares. So this is ultimately giving you VRMS. The root means square velocity. First find the square of the velocities, then add up the squares of the velocities, then find the mean by dividing the sum of the squares by n number of molecules, then find the square root of the entire thing, and that will ultimately give you VRMS. Root means square velocity. Understood? Now without any further ado, let's move into the derivations stepwise. So in order to do the derivations, we need to draw this figure. What is this figure actually? I'm clarifying, so please try to understand. All we are doing is assuming a cubical container of a gas in the three-dimensional space, that is in the space between the x, y and z axis. And you can see this is the x-axis, this is the y-axis, and this is the z-axis. This is a cubical container in which a particular gas is kept, and here also we are assuming that n number of molecules of the gas are kept within this container, and the mass of each molecule is m. And so its n number of molecules are kept within this cubical container, and the mass of each molecule is m. This is of course a particular gas, so the mass of each molecule is supposed to be same. Mass of each molecule is m. Alright, so now just remember the postulate of the kinetic theory of gases, that is, the molecules of a gas are constantly in random motion along straight lines. Another important thing I missed to mention is that each side of this cubical container is taken as A. Alright, length of the edge of this cubical container in the 3D space that we have assumed is A units. N number of molecules of this particular gas are striking with each other as well as with the wall of the container. So now if I assume a particular molecule over here of mass m, the black dot that you can see inside this cubical space is a particular molecule that we are taking into consideration in order to have the equation successfully derived. If this molecule is having a velocity v1, then this velocity is supposed to have its corresponding three rectangular components along the x, y and z directions, isn't it? I'm trying to show you this with the help of another diagram. Now have a look at this diagram. So this is all I wanted to show you. If v1 is the velocity of the molecule we are taking under consideration for this derivation, then v1 is supposed to have the three components along the x, y and z directions. Along x direction the component is v1 subscript x, along y direction it is v1y, along z direction it is v1z. Now see, have a look at the description I've written. Since the molecules of the gas are moving in space, the velocity of each molecule will have three components along the x, y and z axis. So let the velocity v1 of the molecule taken under consideration be resolved into its corresponding x, y and z components as v1x, v1y and v1z respectively. So v1 vector equal to v1x I cap, v1y j cap plus v1z times k cap. And you all know that that's how we can always represent a vector in terms of its x, y and z components. The modulus of v1 vector is equal to under root of v1x squared plus v1y squared plus v1z squared, isn't it? So after that, squaring both sides, we get v1 square is equal to v1x square plus v1y square plus v1z square, if this is one particular equation. Now see the logic. This is also based on a particular assumption of the kinetic theory of gas. Now as the gas molecules are moving in space in totally a random manner, their probability of colliding with the walls of the container on either of x, y and z direction is same. So the x, y and z components of the velocity v1 can roughly be taken to be equal. That is v1x is equal to v1y is equal to v1z. Just imagine the case. The molecules are moving in such a random manner that the possibility of undergoing the collision with either of the three surfaces, with either of the walls of the container on the x, y and z direction is same. Okay. On the basis of the possibility, the probability of collision, we can just consider the x, y and z components of the particular velocity to be roughly equal. So if v1x equal to v1y is equal to v1z, then this particular equation, which I have named as equation 1, can take the form v1 square is equal to 3 times v1x square, because in place of v1y and v1z I put v1x, right? So 3 times v1x square. So v1x square is equal to 1/3 v1 square. So this is a relation which we are going to require in deriving the kinetic gas equation afterwards. So keep a note of it. Keep a note of the entire thing and keep a note of this relation particularly, which I've put inside the box. Now again, let's move into the derivation, the main derivation. If the velocity of the molecule we are considering here is v1, it is having the three components, the one I told you right now. v1x, this is v1y, and along the z direction it is v1z. Okay, so now here I'm gonna consider only the x component of the velocity. In terms of only the x component of the velocity, I'll find out the pressure first. After that, I'm going to normalize the expression in terms of the velocity v1 itself. Alright, because based on the assumption I just explained you right now, that the probability of the molecule to collide with the walls on all sides is almost same, because the motion of the molecule is so random in nature, so the probability of its collision with the walls on all sides, that is all directions x, y and z, is same. So the components of the velocity can be taken to be roughly equal. This is just an assumption, keep it in mind. Okay, the component of the velocity may not be exactly equal, but it is just an assumption, because the motion of the gas molecules is so prompt and so random in nature that it can roughly be taken to be equal. This is just an assumption, so which we have to abide by, and based on this assumption only we shall get at the equation, the kinetic gas equation, P is equal to 1/3 rho v r and so. Alright, so v1x is the component of the velocity that we are taking into account right now, that is the x component of the velocity. And the surface, the wall of this container we are considering is this one, the shaded one. Okay, shaded wall of the cubical container is the one we are considering for the collision, because the x component of velocity I'm taking, so the wall on the direction of the x-axis is this one, the shaded one. So just imagine this molecule is coming in the x direction with a velocity v1x. Alright, with the velocity v1x, this molecule is coming and colliding with this wall. After the collision is over, it is bouncing back to the same direction from which it had come with a velocity minus v1x. Because another assumption is coming into consideration: the collisions of the gas molecules among themselves and with the wall of the container is perfectly elastic in nature. Elastic collision you might have already studied in chapter work, energy and power. In elastic collision thing, what happens is that kinetic energy remains conserved. There is actually no loss of kinetic energy. Alright, so the velocity is just going to reverse the direction from positive x direction into the negative x direction. So the sign will change from plus to minus. v1x will change into minus of v1x. Keep it in mind. I'm drawing this particular figure in order to make it easier for you to understand. If this is the surface of the wall, okay, on which the molecule is colliding, if this is the wall on which the molecule is colliding, this is the molecule of mass m, imagine, and it is coming in this direction with velocity v1x, right? It is colliding here, coming here, it is colliding, it is bouncing back in this direction with velocity minus v1x, right? After the elastic collision on this surface, the molecule is rebounding with velocity minus v1x. After the collision on this surface, that is this surface, the molecule is rebounding with velocity minus v1x. It is going to strike with this wall. After striking with this wall in the YZ plane, it is going to come back again in the same direction with velocity v1x. Alright, so if this is v1x, this is going to be minus v1x, right? So with v1x velocity, the molecule is coming and striking with this shaded wall. It is rebounding after undergoing the perfectly elastic collision with velocity minus v1x and moving to collide with the back wall. After the collision, it is coming back again to collide with the shaded wall. How much is the distance the molecule is traveling? Molecule is traveling a distance equal to a plus a, right? After the collision is done here, the molecule is moving with velocity minus v1x and traveling a distance a equal to the length of the edge of the cube. Then it is colliding with the back wall and coming back again and is about to collide with the same wall and traveling a distance a. So right after the collision over here, it is traveling a distance a and colliding with the back wall. Again it's coming and traveling a distance a, just about to collide with the same wall again. So in between two consecutive collisions, how much is the total amount of distance the molecule is traveling? A and a, right? A plus a, that is 2a. 2a is the amount of distance it is traveling in making one complete collision. So just after the collision over here, the second collision is just about to occur here, but in before that, from just after the end of this collision up to the moment it is just about to make another collision, how much amount of distance it is traveling? A plus A, right? That is 2A. So if the velocity of the molecule is v1x, that is the x component of the velocity we are considering here, how much is the time that the molecule is taking for one collision? Time taken by the molecule to make one collision, time taken by the molecule to make one collision that is delta t is equal to total distance by the velocity away from the shaded wall. It has traveled a distance a, and after colliding with the back wall it has traveled again towards the shaded wall and traveled a distance another a plus a is equal to 2a with the velocity v1x. So the time taken is 2a upon v1x, right? Now how much is the change in momentum? In order to consider the change in momentum, we need to understand the initial and the final value of momentum. The moment the molecule is coming to collide towards a shaded wall, it was coming with a velocity v1x plus v1x, right? So the initial value of momentum pi is equal to m into v1x, and the final value of momentum pf is equal to minus m into v1x, isn't it? Because after the collision is done, it is rebounding with a velocity minus v1x. Alright, so final value of momentum is minus m v1x. So how much is the change in momentum? How much is the change in momentum? Change in momentum, that is delta p, is equal to pi minus pf, initial value of momentum minus final value of momentum, that is 2 into m v1x, right? You may subtract pi from pf, that will give you minus 2 m v1x. So now this is actually the change we are taking into consideration, so we need to take the numerical value, not the sign is important here. Now you tell me how to calculate the force exerted on the wall. Force exerted on the wall F. Now say, how do we calculate the force? Force is calculated by the change in momentum divided by the change in time, isn't it? Change in momentum by the change in time. So how much is that? 2m v1x divided by 2a by v1x, isn't it? So how much is that? M by a v1x whole square, right? Now just remember the relation I told you to keep in mind. This is this one, V1x square is equal to 1 upon 3 into V1 square. This is the relation we're supposed to make use of right in this step. So just put that value. V1x square is equal to 1/3 V1 square. 1/3 V1 square. So m by a times 1/3 V1 square. Alright. Now just imagine this is the force exerted on the wall, on the shaded wall by one particular molecule only, the one we have considered, of mass m and velocity v1. Now how much is the net force which is exerted on the wall of the container by all the molecules? Force due to n number of molecules, how much is that? Force due to n molecules. F net equal to 1/3 m by e v1 square plus 1/3 m by e v2 square plus dot 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 up to the nth molecule 1/3 m by e vn square, isn't it? 1/3 m by a v1 square plus 1/3 m by a v2 square plus dot 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 up to 1/3 m by a vn square. So now we can take out common 1/3 m by e, isn't it? 1/3 m by e, if I take out as common, what is remaining? Is v1 square plus v2 square plus dot 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 up to vn square, right? That's all that is remaining. Now if I divide and multiply this thing with n, then the thing is literally remaining same, isn't it? I'm dividing this entire thing within bracket by n, also multiplying by n. That is all I can do, right? So this is remaining the same thing. Now just have a look at the thing inside the bracket. What is it? What is it actually? Isn't it Vrms square? What was the value for Vrms? Have a look again. Vrms was under root of v1 square plus v2 square plus v3 square plus dot 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 up to vn square divided by n. Under root of this entire thing, v1 square plus v2 square plus v3 square plus dot 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 plus vn square divided by n. And so if I square both sides of this expression, it gives me Vrms square equal to v1 square plus v2 square plus v3 square plus dot 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 up to vn square divided by n, isn't it? So this is all I have got over there inside the bracket. Have a look at this. Vrms square equal to v1 square plus v2 square plus dot 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 up to vn square divided by 3. That's all I've got there, isn't it? See again. Inside the bracket I have got v1 square plus v2 square plus v3 square and so on up to vn square divided by n. This can be written as Vrms square 1/3 m by a times Vrms square times this n is left, this n, okay? So F net, the net force exerted on the wall of the container by all n number of molecules, is equal to 1/3 Mn by A times V RMS square. Alright, now see how do we calculate the pressure. How do we calculate the pressure P? We calculate the pressure by dividing the net force by the surface area of the wall. So P is equal to F net by area. How much is the area of one face of a cube is equal to the length of the edge squared, isn't it? Side into side, the area of a square, because each face of a cube is square in shape, isn't it? So we are getting in numerator 1/3 Mn by A V RMS square divided by A square, A into A, the length of the edge is A, that's all we had assumed. So ultimately this is giving you 1/3 Mn by A cube into V RMS squared. What is a cube? A cube is nothing but the volume of the cube, isn't it? A cube is nothing but the volume of the cube. So P is equal to 1/3 Mn upon V. Now you tell me, what is this Mn? What was M? M was actually the mass of a molecule. The mass of each molecule I had assumed as M. The mass of each molecule I had assumed as M, and N was the number of molecules, the entire number of molecules. Okay, so how much is this Mn? Mn is giving you the mass of the gas contained inside, because the mass of n number of molecules, the gas contained within the cubical space in 3D was having n number of molecules in total. So mass of each molecule is m multiplied by n is giving you the mass of n number of molecules, that is the mass of the gas as a whole. Mass of the gas enclosed. So the mass divided by the volume, a cube is giving you the volume. Volume occupied by n molecules, or volume occupied by the gas. Okay, so now P is equal to 1/3 M upon V. This is actually capital V, don't make a confusion. Capital V means the volume, and this small v subscript RMS means the RMS velocity. Alright, so now we have already arrived at the relation P is equal to 1/3. What is mass by volume? Mass by volume is nothing but the density of the gas. Mass by volume is density of the gas, which is rho times V RMS squared, right? So this is the relation we wanted to prove. We have already arrived at the relation. So you are sometimes asked to prove the relation, which you can get from here. V RMS square is equal to 3p upon rho, isn't it? From here you can get V RMS is equal to under root of 3p by rho. So this is also another relation. So this is the relation that is popularly known as kinetic gas equation. P P is equal to 1/3 rho V RMS square. P is the pressure of the gas, is equal to 1/3 of rho, that is density, into V RMS square, that is RMS velocity of the gas squared. And this expression gives you the value for RMS velocity is equal to root over 3P by rho, 3 times the pressure of the gas by the density of the gas. Hope this video is going to be helpful to you. Hope you could follow all I had tried to explain. And thanks for watching. Take care. Goodbye.